Hi, in this video, we want to talk about inverse matrices and positive definite matrices. Okay, so first thing I want you to think about is the number 0 and addition. Okay, so if I have a number, I add 0, what do I get back? The original number, right? Okay, yeah, you know this. Okay, think about multiplication and the number 1. All right, so if I take a number, multiply by 1, what do I get back? The original number, right? Okay. So both operations have an element among the set that they operate on, such that anything along with that element under that operation gives us the original item. Okay, well, anything with a special property of basically doing nothing under an operation is called an identity. All right, so when we talk about matrix multiplication, if I take the square matrix with zeros above the diagonal, zeros below the diagonal, and ones along the diagonal, that's called the identity matrix. Multiplying by the identity matrix does nothing. Like if I take a matrix, multiply by the identity, I get the original matrix back. There's no change. All right, so algebraically, this is a big deal. This is very important to us. There's a lot of reasons why this is going to be important throughout the course. This is a critical concept. Okay, so the next thing I want to talk about are inverse matrices. All right, so in addition, if I take a number, is there another number that I can add with it to get 0, the identity, under addition? Well, yes, I just take the negative of the number, add them together, boom, I get 0. Okay, what about multiplication? Okay, so I take any number, almost any number, almost, and I multiply it by its reciprocal. Okay, well, what happens? Well, I multiply it, and we get 1, the identity element. Okay, so when I'm talking about addition, the inverse is just the negative of the number. When I talk about multiplication, the inverse is the reciprocal of a number, but there's something special about that multiplication one. Number 0, like I can't take the reciprocal of 0. So 0 does not have a multiplicative inverse. Okay, well, I know you're shocked. This is amazing. Well, what we want to focus on right now, we want to talk about matrices where if I multiply by some other matrix, a special matrix, a particular matrix, I'll get back the identity matrix. Well, it works out that when I have matrices, a lot of them do square, and this only applies to square matrices when we talk about inverses and identities and stuff like that. Well, when I'm talking about matrices, it works out that a lot of them don't have an inverse, so that when I take the matrix, multiply by the inverse, I get the identity. So if A is full rank, it's a square matrix, then there exists another matrix such that if I multiply the two together, I get the identity matrix. And it doesn't matter if I multiply on the left or on the right. I get the identity either way. That's an algebraic property. Now, realize that not every square matrix has an inverse. It has to be one that is full rank, and it has to be a square matrix. So if A is not full rank, then there does not exist a matrix to multiply by it to get the identity matrix. Okay, so let's take an example. Here's an example that is important for dynamics on a torus, believe it or not. A is equal to 1, 1, 1, 2. Its inverse is 2, -1, -1, 1. Okay, well, if I multiply these two together, I can see, and I just go through, I do the operation, I do the addition, I do the multiplication, all that jazz, I get 1, 0, 0, 1, the identity matrix. Now, here's a theorem for us. Multiplication by a full rank matrix does not change the rank. We're going to use this theorem a lot in this chapter. So if B and C are full rank matrices and the multiplication that we do is defined, the rank of A times B is equal to the rank of A, and the rank of C times A is equal to the rank of A. All right, so multiplying by a full rank matrix does not reduce the rank. Okay, so let's go this way. What we're going to do, we're going to prove this for B, and then C really just follows from rewriting things on the other side of the matrix. B is full rank. Therefore, from what we just said a moment ago, the inverse of B exists. Okay, well, I know that B is full rank. B has an inverse. So if I multiply B times B inverse, I get the identity matrix. That's by the definition of the inverse. Okay, well, the rank of A is equal to the rank of A times the identity, right? Because multiplying by I does nothing. So A times I is the same as A. Well, if A times I is equal to A, then the rank of A is equal to the rank of A times I. Okay. Well, I is the same as B times B inverse. Okay, well, let's do that. So A is equal to the rank of A times B, B inverse. Now, we have a theorem from a previous section in the textbook that if I basically drop either on the far right-hand side or on the far left, if I drop a matrix from the product, the rank is either the same or greater. So if I drop this inverse part, the rank of AB has to be greater than or equal to the rank of A. Okay, well, I can drop B also. So if I drop the B part again from here, the rank can only increase. Either it's the same or it's greater. All right, so by going through this chain, I see that the rank of A is less than or equal to the rank of A times B is less than or equal to the rank of A. Well, the rank of A is on both sides of an inequality, right? The rank of AB is greater than or equal to the rank of A, and the rank of AB is less than or equal to the rank of A. It is greater than or equal to or less than or equal to the same thing. All right, so it has to be equal to. So the rank of A is equal to the rank of A times B. Now, for the rank of C times A, all we do is just basically rewrite this, but I put I on the left-hand side of A at the beginning. I run through it, same concept. It's beautiful. It's beautiful. All right, so now let's talk about systems of equations. If A is non-singular, then for any vector C, there exists a unique solution to this equation. So remember, when I say non-singular, that automatically means we're talking about square matrix. So something that's going to happen from here on out in the rest of the course, I'm going to say something, and the definition of that term is going to imply certain properties. And it's going to be on us to be aware of those properties. So when I say non-singular, you know that's full rank, you know that's square. And it's hip to be square. Okay, so we know that there exists a unique solution to this equation. A times some vector is equal to the value we're interested in. In fact, the solution is going to be A inverse times that vector. And that's it. All right, so here is a theorem for us. If A is non-singular, remember it's square and full rank, then A transpose is also non-singular. And furthermore, the inverse of A transpose is equal to the transpose of A inverse. This is going to be a very convenient fact for us. That means that we can bounce back and forth. And you'll see some authors that when they deal with this, they'll put actually a negative T in the superscript because it doesn't matter if we're doing the inverse or the transpose first. All right, if A and B are non-singular matrices of the same size, then A times B is non-singular, and furthermore, the inverse of A times B in parentheses, inverse, is equal to inverse B times inverse A. And the proof of this is super, super simple. Now I'm thinking about it. Yeah, it's just A times B, B inverse A, inverse, and boom, you got it. It's easy peasy, lemon squeezy. Okay, so now let's talk about block matrices. When I've got a block matrix, let's say that A is equal to A11, A12, A21, A22. And remember that each of these capital letters represents an entire matrix. And we're implying that the dimensions line up, that this is a coherent matrix. All right, well, if I let B equal A2 minus A21, A11 inverse, and A12, if A11 inverse and B inverse exists, then A inverse is equal to this formula. So we see that we have kind of ugly, but it's going to be A11 inverse plus A11 inverse A2 B inverse A21 A11 inverse. Here we're going to have negative B inverse A21 A11 inverse. Here we get almost the same thing, but the subscript is switched on the middle. So it's negative A11 inverse A12 B inverse. And then down here we just get B inverse. Whew, that's a lot to say. Okay, okay. Well, let's look at a special case. If A is a block diagonal matrix of this form, then the inverse of A is the block diagonal with the inverse matrices. And that's pretty easy to show. And this generalizes to block matrices, diagonal block matrices of any size. All right, next thing we want to talk about are positive definite matrices. All right, positive definite matrices are matrices that if I take a vector, I multiply with the transpose on the left and the vector on the right and the matrix in the middle, if it's positive definite, that number is always going to be positive that I get. Okay, so what we want to look at is, at this point, I could, so I could go y transpose a y, right? That's interesting. We don't really see why that's important, but this is going to be important to us later down the road. Well, you'll notice that if I go through and instead of having a, I go a plus a transpose divided by 2, then I'll actually get the same thing when I put the y's on each side. So if I go a plus a transpose over 2, put the y's on each side, I'll get the same value as I get up here. Why do we care about this? Well, this a plus a transpose business is going to automatically be symmetric, and it's going to have some nice properties that will be advantageous for us when we do numerical linear algebra. All right, so this a plus a transpose is always symmetric. And it's going to be a symmetric matrix such that this y transpose a y is going to be greater than 0 for all y not equal to 0, as long as a is positive definite. Now, if I take this y transpose a y, and it's greater than or equal to 0, then it's called positive definite. Now, something that's important is to remember when we look at these products, y is not equal to 0. Because if it's equal to 0, then we just get 0. And I mean, that's not really interesting. That's stupid to worry about. All right, so if A is positive definite, then all the entries along the diagonal are positive. All right, so for a proof, let's say that we just take this standard basis vector that I have 1 in one spot, 0 everywhere else. And it corresponds to the ith position. The ith position is 1, and I want to show that a sub ii is greater than 0. Well, if I go through and I do this multiplication, on the right, I'm going to get the ith column. And then on the left, I get the ith row. Well, if you think about that for a moment, that's just going to give me aii. A is positive definite. Therefore, no matter what I do, I have to get a, I have to get a non-zero, a non-negative number. It has to be a positive number here because it's positive definite. So this has to be positive. Therefore, this is positive, which means that I get my result. Now, if A is positive definite, that means I can multiply on the left and right by a vector, so y transpose AY. That will give me one number. So that's what positive definite means, and that number will be positive. Let's say that A is positive definite, P is non-singular, so it has an inverse, then P transpose AP is also positive definite. All right, so now let's prove this. All right, what we need to do, we need to show that I can take any non-zero y vector, and this should be all y. Y is not equal to 0. Oh, here it is. I got it right there. If I multiply it on the left and right for any given y that's not equal to the 0 vector, I need to get a positive number to prove this. Okay, so I go y transpose times the thing in the middle, y. All right, what I'm going to do, we have an associative property in matrix multiplication, which means I can change the order of the parentheses, just like we can with numbers and when we're doing only multiplication. So notice I don't have any addition going on in this business. The only operation here is multiplication. That means I can change the order in which I do my parentheses freely. Okay, so what I'm going to do, I'm going to put the y transpose, p transpose together. I'm going to put p and y together, and boom, I've got this. Okay, well, remember that if I have something transpose times something else transpose, if I can switch that, I can pull the transpose outside this parenthesis if I put p before y. And so if I do that, I can see that this multiplication becomes p times y transpose. Here I've got p times y, and I've got a in the middle. All right, so that means that p times y is actually that vector on each side of the matrix. Well, if I have a vector on each side of the matrix, I go ahead and say that v is equal to p times y, then this is what I've got. Well, a is positive definite, so I know that this is positive. Therefore, this is positive. Therefore, this is positive, and therefore, the thing I was working with originally is positive. We've got it. So here we can see that p transpose AP, if I multiply each side by any non-zero vector, I'm going to get a positive number. All right, here's a corollary. If A is a p times p square positive definite matrix, B is k times p, k is less than p, rank of B is equal to k, then B times A times B transpose is positive definite. All right, so if I think about this for a moment, I've got B, A, B transpose. All right, so this is going to be a k by k matrix when I'm all done. I'm saying that the rank of B is k. Okay. Now, if I look at this next one, for a symmetric matrix, it will be positive definite if and only if there exists a matrix that I can factor A into as P transpose P. Okay, so a matrix, a symmetric matrix is positive definite if and only if I can factor it into P transpose times P. Let's go ahead and prove the going from the right-hand side to the left-hand side. All right, so we're going to assume that I can factor A in the special format. P is non-singular by assumption, and A is symmetric by hypothesis. All right, so we're going to let Y be any given non-vector. Okay, so a non-zero vector. Then Y transpose T times A Y is equal to this. All I'm doing is taking the A and I'm factoring it in the way that we are assuming that we can do. Okay, well, I'm going to go ahead and use that associative property of matrix multiplication, and I'm going to change the order of the parentheses. That's what I do from here to here. Okay, well, I know that I can pull this transpose out of the parenthesis if I switch the order of P and Y. So I have P, Y, whole thing transpose times P, Y. All right, so these are two vectors. Sorry, this is one vector where I'm taking its transpose and multiplying by itself. All right, so what that's going to end up being, that's going to be I'm going to take the square of the entries of the vector, and so I'm going to take the entries of the vector, square them, add them up. And if I was to take a square root, then that would be what we call the 2 norm, very similar to the Euclidean distance. So here, this is the 2 norm squared of that py vector. Okay, so I know for a fact that that has to be greater than or equal to 0 because I'm squaring a bunch of numbers and I add them up. Has to be non-zero. Okay, now, could it be 0? Well, P is non-singular, right? P is non-singular means that the only way that I can get 0 is if I multiply by the 0 vector. Okay, well, I look up here and we say that y is any given non-zero vector. So y does not equal 0. The only way that I can get p times y to equal 0 is if y is equal to 0, because p is non-singular. All right, so we know that we don't get the 0 vector, which means that this has to be a positive number. This is a positive number, therefore, that y transpose ay has to be positive also. So once again, we get the result. So we can see that A is a positive definite matrix. All right, so one thing that comes out of this is that as a corollary, a positive definite matrix is non-singular. So anytime I have a positive definite matrix, automatically it has an inverse. All right, so let's do another theorem. If B is an n by P matrix, if the rank of B is equal to P, then B transpose B is positive definite. All right, so if the rank is equal to the number of columns, and I multiply the matrix by its transpose on the left, I get a positive definite matrix. Okay, well, let's see what we can do with this. So I need to prove that if I take any non-zero vector, multiply on the left by the transpose, multiply by the right by the vector, and it's any given vector, that I have to get a positive number. All right, so y is not equal to 0 vector. So y transpose B transpose, B times y. So I'm just taking this thing here. I want to show that it is positive definite. So I multiply on the left by y transpose, on the right by y. Boom, I get this. Now I'm going to use the associative property of matrix multiplication to change the order of my operations. So I'm doing parenthesis and parenthesis. Okay, well, once again, I see that if I pull this transpose out, I can switch the order of the b's and y's. So I get by transpose by. Well, we know that that is the sum of the squared entries of b times y. Well, so I know it's a sum of numbers that have been squared. I know automatically it has to be greater than or equal to 0. Okay, so that gets me to here. Now, can it be 0? Well, B is full rank, right? So B has rank P, and that's its number of columns. So it has all linearly independent columns. Has all linearly independent columns means that the only way I can get 0 is if I'm multiplying by the 0 vector. But y is not equal to 0. By the way, we do positive definite. Therefore, this has to be greater than 0. Well, this squared is equal to what we were looking for. Therefore, we know it has to be positive definite. Here's another theorem for us. If A is positive definite, then A inverse is positive definite. Okay, so how we proceed is that let's go ahead and say that A is equal to P transpose P. All right, from our previous theorem, we know that we can do that. We can factor A in this manner because it's positive definite. So P is non-singular. P is non-singular tells me that P's inverse exists. All right, P inverse exists. So now let's do this. I'm going to take the inverse of both sides of this equation. A inverse has to be equal to P transpose P inverse. Now, the inverse exists, therefore I can go ahead and apply the inverse operation to each of these two matrices. But remember, I have to switch the order. Boom, I do that. So now when I get to here, remember that P transpose inverse is the same as P inverse transpose. Okay. So now what I want to do is I want to show that A inverse is positive definite. And I'm going to use this part here. A inverse is equal to this bad boy over here. I'm going to put y's on each side. I'm going to show that I'm going to get a positive number as long as y does not equal 0 vector. All right, so y transpose A inverse y is equal to y transpose P inverse transpose y. It's a lot to say. So I'm going to use exactly the same trick I've been using this entire time. I'm going to pull out the transpose part, but I switch the order. Boom, I got it. I got this. I got this. Okay, so I can see I've got something inside the bigger parenthesis. I have the same thing inside the bigger parenthesis, but there's a transpose. Well, what is this thing inside the big parenthesis? That's going to be a vector. It's a matrix times a vector. Therefore, it's a vector. What properties of a vector? I don't know, and I don't care. But I've got the same thing here. So I have a vector transpose times the vector itself. I know that's equal to the 2 norm squared. Boom, I got it. It's a 2 norm. Therefore, it's a norm. Therefore, it's greater than or equal to 0. Okay, greater than or equal to 0. Made it this far. Now we just have to show it can't be equal to 0. Well, so yeah, so y transpose A inverse y is greater than or equal to 0. So far we've shown that A inverse is semi-positive definite. We want to take that ball across the goal line and make it into positive definite. Okay, so P is non-singular. Oh, so this should just be P inverse transpose. This y is incorrect. I apologize. That should not be there. All right, so pretend that this y is not here. Then P inverse transpose is non-singular also. That's from previous part of the textbook. Therefore, when I multiply, I cannot get the 0 vector unless y is equal to 0. But by assumption, y does not equal 0. Therefore, this cannot equal 0. Okay, so the only way that I can get 0 out of a norm is if I have the 0 vector on the inside. Well, we just showed that what's on the inside can't be equal to 0. Therefore, the norm cannot be 0. Therefore, and the norm is equal to what we were interested in the first place, so it has to be positive. Easy peasy lemon squeezy. All right, if A is a positive definite matrix, then for any partition where we have squares along the diagonal, so I have a block matrix, I have squares along the diagonal, and this the subscript should match. Then the AI, then all of the diagonal matrices are positive definites. Now, the proof of that, all we do is we consider the vector that has one, so if it's not true, proof by contradiction, if it's not true, I find the vector that gives me 0 or negative when I do this y transpose matrix y, and then in the right position, I put that vector, I put 0 everywhere else. And it just boom, 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 it goes. All right, so we're going to take the vector of zeros. So we're doing proof by contradiction. I'm going to take the y such that this is less than or equal to 0. And if this is not positive definite, at least one y exists for achieving this goal. That's not equal to 0. Now I'm going to take the vector where I put y in the corresponding position of the block matrix of AII. I put 0 everywhere else. When I do the positive definite multiplication, it just comes out immediately. Because what will happen is that I get 0, then the block I'm talking about, then 0, which I know has to be less than or equal to 0 because of this aspect. But that means that A is not positive definite in the first place. So that's a contradiction. Boom. That's it. We're done. All right, that's all I've got for you for now. Go through, read the book very, very slowly. Be ready to read this like 8 to 12 times. I'm not joking. You need to read this material very, very slowly. You need to read this like 8 to 12 times. If you ask me questions and you haven't read it 8 times, it's going to be hard for me to help you. This is a very Like, things are going to start getting like really nuanced from here on out in the class. Make sure you read it slowly, you read it repeatedly. If you have not had a rigorous proof-based linear algebra course, you're going to start going through some stuff right now. Take care and goodbye.